The modern automotive industry has rapidly shifted towards software-defined vehicles. These complex systems are driven by high-performance, multi-core systems on chip. This exponential increase in architectural complexity guarantees a rise in unpredictable systematic and random hardware faults. To manage these risks, the ISO26262 functional safety standard mandates a specific design philosophy: the principle of mutual distrust between hardware and software. Mutual distrust requires that neither domain assumes the other is functioning correctly. Both must constantly monitor, diagnose, and restrict each other's execution boundaries. Modern embedded automotive engineering relies on the precision and rigidity with which this distrust is mapped. In many embedded workflows, hardware teams finalize a design and hand over an Excel-based register map to define the system boundaries for the software team. These static register maps provide structural metadata. They list memory addresses, bit offsets, and basic read-write access flags. They tell the software where a hardware component is, but not how it behaves. Under ISO 26262, relying on a static list of memory addresses to ensure system integrity is a violation of safety design principles. The standard requires a hardware-software interface, or HSI. This is a bidirectional safety contract that defines specific behavioral constraints. Confusing a mere structural register map for a behavioral safety contract leads to catastrophic failures during late-stage hardware-software integration. The window Watchdog serves as a proof of this HSI contract theory. It is a hardware safety mechanism designed to detect and reset runaway software. This diagram compares the two documentation styles. On the left, an Excel register map provides memory addresses and a refresh command. It contains no temporal data, leaving the timeline empty. The Watchdog requires a specific sequence executed within a precise open window segment. If software relies only on the static map, scheduling delays push the right command into the red closed window, triggering an immediate system reset. The software executed the correct command according to the register map, yet the result was a system failure. True HSI definitions include access restrictions, ensuring only high-priority safety tasks can reach the Watchdog registers, preventing interference from lower-level software. Without behavioral timing constraints documented as an HSI contract, perfectly coded software can inadvertently trigger hardware resets. We can trace the physical destruction of an EV inverter back to this documentation gap. The component burned out after an overcurrent fault went unhandled. The failure originated in the microcontroller's fault status register. This register reported an overvoltage fault on bit 0 and an overcurrent fault on bit 1. To maximize speed, hardware designers implemented a clear-on-read property. This causes the register to wipe its own data the moment it is accessed by software. This clear-on-read behavior was omitted from the register map, which merely labeled the register as standard read-only. On a microsecond timeline, software detects an alert and initiates a read command on bit 0 to address the overvoltage. At the exact same microsecond, an overcurrent event occurs. Hardware attempts to push a warning flag to bit 1. Because of the undocumented semantic property, reading bit 0 physically deletes the incoming overcurrent warning before the software registers it. This is why HSI contracts must explicitly forbid clear-on-read for fault registers, demanding write 1 to clear to guarantee isolated atomic operations. Semantic omissions in documentation create invisible race conditions capable of destroying hardware. These register failures reflect a larger disconnect between the divergent life cycles of hardware and software teams. Semiconductor tape-out cycles force hardware architectures to be finalized and frozen years before a vehicle reaches the road. Software teams operate on Agile CI/CD cycles, pushing hundreds of iterative releases across that same time span. This leads to register mismatch. Mid-cycle hardware adjustments are often buried in static documents that fast-moving software teams miss. Because memory addresses remain valid, compilers cannot catch these mismatches. The errors stay dormant until physical integration testing begins. This disconnect invalidates FMEDA metrics. The calculated hardware safety math depends on the software behaving exactly as theorized. Hardware safety metrics lose their predictive value if the Agile software cycle drifts out of sync with the frozen hardware architecture. The engineering solution is to replace human-readable text documents with a machine-readable model. SystemRDL provides the necessary language for this transition, as it can capture both the structural map and complex semantic behaviors. By defining the HSI in SystemRDL, engineers can mathematically model timing windows, side effects, and isolation boundaries in a single file. This creates a single source of truth pipeline. This central model hub drives synchronized updates to the RTL code, the C++ headers, and the UVM models. In practice, if a hardware engineer alters a diagnostic bit field in the central model and commits the change, the pipeline instantly triggers a software driver rebuild and regenerates all verification test sequences. This methodology eliminates the fragmented translation process, removing the potential for human error between the hardware and software domains. This automation creates a physical barrier. Hardware and software are now mathematically incapable of diverging from the HSI contract. As vehicles scale toward autonomous driving functionality, the margin for architectural drift disappears. A rigorously modeled, machine-readable HSI is the ultimate structural firewall, protecting human life from systemic collapse.